Hi, everyone. Thank you so much for watching my presentation today. I'm really excited to talk about some of my recent work on ultrafast laser filament-induced fluorescence of a single-celled green algae called Chlamydomonas reinhardti to identify signatures of uranium exposure. So the motivation for my work is remote detection and monitoring for nuclear nonproliferation purposes. And traditionally, ionizing radiation detectors are used, but there are some scenarios in which not being limited to just radioactive materials or being able to monitor signatures more easily remotely could be beneficial. And an example scenario I like to provide is in monitoring for undeclared or clandestinely operated uranium centrifuge enrichment facilities. So because the centrifuge enrichment process is well established and it also doesn't draw a lot of electricity, they can be operated clandestinely, but previous work has found that they do emit UF6, which is the gas used in the centrifuge process. It does emit from these facilities in small quantities, and it reacts rapidly with water vapor in the atmosphere to form a compound called uranyl fluoride. And simulations have shown that once in the vapor phase, uranyl fluoride can propagate hundreds of kilometers away from the original site in varying concentrations. And so uranyl fluoride doesn't emit a lot of radiation or ionizing radiation, but because of its low natural background, it would be a strong signature of enrichment activities. And especially once in the vapor phase, uranyl fluoride can infiltrate the surrounding environment by deposition into surrounding water systems or into the soil and can eventually be uptaken by plants. And so I propose to use laser-based methods for several benefits they have in detection of low concentrations of materials and also remote detection capabilities. And in a cylindrical volume of 1 kilometer height and 2 kilometer radius in this highest concentration region, contains enough uranyl fluoride to potentially deposit a 50 micromolar concentration of uranium in the environment. So for the mission relevance, it's development of remote high sensitivity methods for in-field monitoring. And we use ultra short high intensity lasers because they can enable remote analysis with high spatial resolution by undergoing a process called filamentation. And so essentially when you have really high peak powers, your laser beam can undergo nonlinear optical effects as it propagates through a medium. In this case, it undergoes a process called self-focusing, in which it reaches a high enough intensity to ionize the air and forms a plasma column that actually confines the laser intensity over hundreds of meters and has been demonstrated to be kilometers. It retains a small spot size and a high enough intensity to excite a signature. The other benefit to using ultra short pulse lasers is that they enable resolution of rapid molecular dynamics, in particular fluorescence, which will be interesting and I'll introduce later. So for technical background, in order to monitor plants' health, oftentimes optical properties are used. So when light interacts with a plant, three things can happen. It can undergo photosynthesis, it can emit excess energy as heat, or it can fluoresce. So this fluorescence comes from chlorophyll, which is the main pigment involved in light capture for photosynthesis. It also gives plants their green color. And we propose to use it for in-field monitoring signatures. Chlorophyll also resides in two main sites in the plant's photosynthetic chain, the first of which is PS2 or photosystem 2, which is involved in converting water into oxygen and protons. And the second is PS1, which is involved in another process that signals the second stage of photosynthesis. And the reason I point these out is because the chemical environment in those two photosystems is slightly different, which makes the chlorophyll fluoresce slightly differently when measuring in vivo. And so on the right, you can see that PS2 primarily fluoresces at lower wavelengths, usually below 700 nanometers, but PS1 fluoresces at higher wavelengths, usually 720 and higher. So in order to look for potential signatures of uranium exposure in the environment, I use a uranyl nitrate sample and do a hydroponic nutrient solution contaminated with uranium in order to look at the effects on a single-celled green algae called Chlamydomonas reinhardti. So I picked this algae because it contains a lot of the same photosynthetic pigments as typical higher plants or leafy green plants that you would see above ground. And on the right, I show our example lab setup for the filament-induced fluorescence. So we make blue light from our red laser in order to more efficiently excite the chlorophyll. And you can see we form a filament on a lab scale here, and we place a cuvette holder, which contains a cuvette that holds our algae about 50 centimeters after the filament collapses. And we directly image the fluorescence side on using our high sensitivity camera and some filters. So here I show the example chlorophyll fluorescence spectrum on the right, along with the transmittance of the two filters we use to isolate the two bands in the fluorescence spectrum. And on the left, you can see example fluorescence images where the laser is propagating from left to right. And you can see the edge of the cuvette holder along with the mount for the filters and the aperture in the cuvette holder. And so I integrate the intensity in these images to determine the total fluorescence intensity. Because I'm using a pulse laser with a gated detector, I can also use temporal resolution to gain information about the fluorescence dynamics. And so as you can see in time, the fluorescence decays, it decays exponentially. And so I can use an exponential fit to get lifetime and decay constants. So first I want to show the absorbance spectra of the algae suspended in their culture or nutrient solutions. And so we can see as early as 1 hour after the uranium exposure, there's already a significant change in the absorption spectrum. And that is this increased absorbance in the UV region. So typically photosynthetic pigments don't absorb in the UV, but what do are radical or reactive oxygen species that form when plants are under stress, along with proteins that act as antioxidants. But in order to get information about the pigment concentrations, you have to do a polar solvent extraction. So here on the right, I show the pigments extracted from the algae in ethanol. And so we can use previously defined equations to get chlorophyll A, chlorophyll B, and total carotenoid concentrations from these. So I wanted to compare the relationship between the pigments to the fluorescence parameters that we observed. And so first I'm showing the 675 nanometer time integrated intensity on the top, the time integrated 720 nanometer intensity on the bottom, and their relationship with the carotenoid concentration. And so we can see for both the control and the uranium exposed samples, we see with increasing carotenoid concentration, there's a decrease in fluorescence intensity. And so this isn't surprising. It could be a result of non-photochemical quenching by carotenoids. We also look at the relationship with chlorophyll A and see that there's also a slight relationship here. However, it's less strong, but we were curious to look at it because chlorophyll A does tend to reabsorb fluorescence as it's emitted from samples. But where we really see an interesting relationship is when we compare the carotenoid concentrations to the lifetimes. And so first, if we look at the control case, we see with increasing carotenoid concentration, there's a decrease in fluorescence lifetime. And this matches what we would expect for non-photochemical quenching, where chlorophyll A transfers its energy to carotenoids for it to dissipate of. But when we look at the uranium exposed samples, we see with increasing carotenoid concentration, there's an increase in fluorescence lifetime. And this would imply a decrease in non-photochemical quenching. But we think that this is likely occurring because carotenoids also act as antioxidants in the plant. And so because there was evidence of radical and reactive oxygen species forming in the absorbance spectrum, we believe the carotenoids are also doing that in the uranium exposed plant. And so because they're acting in that way, they're essentially not available to undergo non-photochemical quenching. We also wanted to look at the temporal profile as a potential remotely distinguishable feature because from the previous slide, we saw that the uranium samples generally had a longer lifetime. And so we integrate a segment of the temporal profile and take the ratio of that with respect to the total temporal profile and find that we are able to discriminate those with 1 sigma uncertainties, which I show here in the middle plot. And so we can use uncertainty propagation and extrapolate out that uncertainty to longer distances and see really what is the maximum distance we could distinguish the control samples from the uranium samples. And so we can use the mean and 1 sigma uncertainty to generate Gaussian distributions and calculate detection probabilities, which is the uranium distribution, and false alarm probability, which is any control distribution that falls above a critical limit. And so you see those detection and false alarm probabilities on the right, and we're able to determine a 90% detection probability with a single laser shot per time step at 35 meters, but we have to average more laser shots together to achieve 95% detection out to even greater distances. And so with 100 laser shots, we can determine 95% detection out to 125 meters, which is equivalent to about a 1 second measurement time. So the impact of this work is development of in situ environmental monitoring. So you can imagine mounting a laser onto a UAV drone, for example, and being out surveying an area, exciting chlorophyll fluorescence signatures, and looking for some relationship with the fluorescence lifetime that might be different than other areas. So the MTV impact, I've been able to participate in workshops and UPRs over the past 4.5 years, networking with other students and scientists, which has influenced my PhD work. For example, I met Dr. Laura Tovo from Savannah River National Lab at the 2020 MTV workshop, and she became a member of my dissertation committee. So in conclusion, I've demonstrated non-destructive filament-induced fluorescence of live algae for the first time and identified a potential parameter that could be used to remotely distinguish uranium exposure in the environment. But we would like to implement higher sensitivity methods in order to understand specifically how the uranium stress is inducing changes in the optical properties, for example, the non-photochemical quenching and fluorescence. So with that, I'd like to thank our sponsors, and I'll thank you all for your time for listening. Please feel free to reach out with questions, and thank you so much.